Hello everyone and welcome back to PC Retro Programmer. In this week's video we're getting back to drawing the general ellipse, and we're doing this on an IBM PC from 1981 with a color graphics adapter and with an 8088 CPU, and we're going to write it in assembly language. Now remember that a standard ellipse is one with the axes aligned vertically and horizontally, and a general ellipse is just one that's rotated. So what we're going to do in this week's video is figure out a few things that we need before we can actually start drawing the ellipse, and then do a little bit of experimentation to try and figure out what could go wrong, and this will help us to plan our approach. So the first thing that we need to do is to take a look at the equation of the ellipse and make some simplifications and compute some points that are going to be important for drawing the ellipse. Now this is going to involve just a little bit of maths, but not to worry, I'm not going to go through all the derivations in detail. I'll give you enough information so that you could do it yourself if you know all of that stuff, but for everybody else, the main point would just be that we can actually figure these values out and we can write them down. And then we'll start to experiment with these values and see where things go a little bit askew. Before we jump into the maths, I wanted to discuss one option which seemed quite popular, and that is to draw a skew ellipse. So a skew ellipse is a standard ellipse that's been skewed. Basically what you do is you draw a standard ellipse and then you skew all the points. Essentially, the further you are from the center of the ellipse, the more you push the points in, let's say, the horizontal direction. And the result ends up looking like a standard ellipse that's been rotated, which is exactly what a general ellipse is. In fact, it turns out that every skew ellipse is the rotation of some standard ellipse. Not the standard ellipse that you skewed, but the rotation of some standard ellipse. So if we could actually figure out the relationship between the general ellipse that we want and these skewed standard ellipses, we'd have an algorithm for the general ellipse. Now that sounds good in theory, but in practice there's a couple of problems. First of all, we don't actually have an algorithm for drawing a skew ellipse. We have an algorithm for drawing a standard ellipse, and this makes approximations. We can't pick points that are exactly on the ellipse. We have to pick the pixels that are nearest to the ellipse, and this means that in practice we could be anywhere up to half a pixel away from the true points on the ellipse. So there's a half pixel approximation there. And when we do the skew, there's another approximation. The skew will be by some fractional amount in, say, the horizontal direction, and we have to pick the nearest pixels to the skew that we want. And so that's, again, another half pixel approximation. And it can happen quite often that these two approximations get added together, and so we can end up with pixels that are up to 1 pixel away from the true pixels on the ellipse. Now it doesn't sound too bad, but if you wanted a perfect ellipse, you should pick points that are at most half a pixel away. If you're picking them 1 pixel away, it could mean that you're picking the wrong pixels. And so the result will in general end up looking a little bit jagged. Now the other problem with this is that when you do the skew, points which were close to each other on the original ellipse can now end up being pulled apart, and so there can actually end up being gaps in your ellipse. Now one way to work around that is just to draw an ellipse that's twice as large and then divide all the coordinates by 2 before you plot them. And this actually works in practice. We can use the same trick that we use for our circle drawing to do this without actually needing bigger registers in the CPU. The problem is that we're doing twice as many points now, and it's going to take twice as long. So basically we end up with an inferior result that takes twice as long, and I haven't even taken into account the amount of time for the skew itself. So this will end up being the less desirable option if we can figure out how to do it properly using the equation of the general ellipse. So that's why we're going to pursue that approach first, and if we don't make any progress with that, we'll come back to the skew ellipses. That being said, let's dive into some of the maths that we need to analyze the general ellipse. Now, to make up for the fact that I'm actually going to show some equations in this video, which is surely going to bring back bad memories for some viewers, I've got a little bit of a surprise later in the video. I found some really cool graphical software online which runs in the web browser, and it's great fun to play with. It only does one thing essentially, but it does it really, really well. So we have that to look forward to. But for now, let's look at some maths. So the idea in this video is that we want to compute just 8 points on the ellipse. They'll turn out to be very important points. It won't matter how we compute them essentially. It can take a little bit of time if necessary because there's only 8 of them. But we will need these, and they're motivated by what we did for the standard ellipse. We discovered that it's actually much easier to draw an ellipse if you break it up into segments that are more or less traveling in the same direction. For example, you might have a segment that's traveling always up and to the left, or always down and to the right, and so on. And if you break an ellipse up this way, you'll break it into 8 segments. Now, what we want to do is compute the start points of each of those segments. It turns out that from there, it's actually exactly the same algorithm as we used for the standard ellipse. We'd even be able to use the same code if we didn't have some other complications. Of course, we have different starting values and different constants, but it's essentially the same algorithm to draw any of these segments. So the real key is to be able to compute these endpoints. Now, what are the endpoints going to be? Well, basically what we want is the points on the ellipse where the line starts traveling vertical, or where it starts traveling horizontal, or at 45-degree angles. So that'll give us the 8 points that we want to draw, the endpoints of our segments. Now, in order to do this, we start with the equation of the general ellipse, and it looks like this. Actually, this is the equation for a conic section, and you have to pick these constants b, a, and c such that b squared minus 4ac is less than 0. This is an important value. It's called the discriminant, and it's sometimes written with a little delta symbol here. And it's actually going to pop up already a little bit below, and so this is actually quite an important value for us. But if that's less than 0, you'll get an ellipse. If it's equal to 0, you get a parabola or maybe some straight lines. And if it's greater than 0, you'll get a hyperbola. And I'll actually show this a little bit later in the video. So we basically have this equation with 6 constant values here, a through f, and we will pick those. So they're going to control the shape of the ellipse that we want to draw. And this is a little bit inconvenient having 6 constants, but it turns out that there's a little trick that we can do to get rid of 2 of them. So at the moment, we haven't actually picked where we want the origin to go, the 0, point. And if we draw an ellipse such that the origin is right bang in the middle of the ellipse, then we can actually make a simplification. An ellipse with the origin right in the middle has some symmetry. Basically, if you change the x-coordinate for minus x and y for minus y at the same time, then you'll get the same thing. There's a kind of reflection that goes on, and this is what the reflection looks like. So if I actually put these values, minus x and minus y, in for x and y in this equation, what I end up with is this equation here. It's exactly the same, except this plus and this plus become minuses. And so this must also be the equation of any ellipse centered at the origin. So now we have two equations that our ellipse has to satisfy, and we can just subtract them. And if you do that, you find out that dx plus ey has to be 0. Now this is really cool because it means we can just throw those terms away, and what we're left with is a much simpler equation. And so this is actually the equation for an ellipse centered at the origin. So that's the first simplification that we can make. Now, as I hinted in the previous video, in order to compute the endpoints of the segments that we're interested in, we need to look at the slope. Those endpoints are going to be precisely at the points where the ellipse is horizontal, or the slope is 0, where the ellipse is vertical, or the slope is infinite, and at the 45-degree slopes, so basically where the slope is 1 or -1. And it turns out that there's a gadget that we can use for computing slopes from calculus called the derivative. Basically, the derivative gives you the slope of a curve. And we write it as dy dx. So that means the derivative of y with respect to x. So how do I actually use that to calculate the slope? Normally when we do derivatives, we have y is some function of x, and we just compute the derivative of that function in terms of x. Here we don't quite have that, and it'd actually be a lot of fuss to rewrite this as an equation with y expressed as a function of x. It would be very messy, and it would also be very hard to differentiate. But it turns out that there's a trick we can use called implicit differentiation. Basically what we do is we go through and think of each of these terms as a function in x, and we differentiate it term by term. Now, the way this works is that we start off with this term here. The constant would just be retained, so we just need to compute the derivative of x squared with respect to x. And there's a rule for that. You take the power at the front, and then you drop the power by 1. So we just end up with 2ax for that term. Now, the next one's a little bit more tricky than this. We have to think of this as a product of two functions in x. The first function is just the function x itself, and the second is y, which we think of as a function in x. And basically, we need to use a rule for computing the derivative of a product of two functions. That's called the product rule. And it's very straightforward. Basically, you just take the derivative of the first function and multiply by the second function, and you add to that the first function multiplied by the derivative of the second function, and that gives you two terms in this case. Now we don't bother to actually compute the derivative of y with respect to x, we just write it down as dy dx. After all, that's the thing that we're interested in, and we'll be able to solve this equation to get at it. Now the next term we could handle in exactly the same way with the product rule. You just think of y as a function of x, and it's just multiplied by itself. Or there's another rule called the chain rule that allows to get it directly. Either way, you end up with this term here. And derivative of a constant is always 0, so that just goes away. So we get this equation here, and believe it or not, all the really hard work is done at this point. Well, apart from some algebra, but I did that using a computer algebra system. I certainly didn't bother doing it by hand. So basically, now that we've got this equation here, which allows us to solve for the slope, what we're interested in is the points where the slope is one of these four values. So we could just go ahead and plug in slope equals 0, and that'll mean dy dx is 0, which will get rid of both of those terms, and all we'll be left with is 2ax plus by is 0. And that's where I got that equation from here. Now this is really cool because it means that at the point on the ellipse where the slope is 0, this value will be 0. And this is really easy to work with. I can actually solve this and write this as y in terms of x. And it's just basically a linear equation, which is really easy. And I can then plug that y in terms of x into my original equation for the ellipse, and that'll make the y's go away because I've just replaced them all with this function of x that I computed here. And what I end up with is just a quadratic equation in x. And this is cool because you can just look up the solutions for those on the web. There's just a formula for it. You don't even have to remember it. So we can compute the roots of the quadratic equation you end up with, and this will give you two values of x. And it turns out that those values are, this is where I use the computer algebra system, plus or minus the square root of this here. This delta, by the way, is the discriminant, which we talked about earlier. It just pops up here. And so we have two values of x, and these correspond to the 2 points on the ellipse where the slope is 0. Now, how do we compute the corresponding y coordinates? Well, that's actually really easy because we've got this equation here. We just plug in these two x values, and for each x value we'll get a y value when we solve this equation. And so that'll give us the y coordinates corresponding to those x coordinates. Now, I didn't bother checking whether these should both be the same sign or both opposite signs or whatever, but there's just 2 points here. It makes it look like there's 4 because there's plus or minus and plus or minus, but actually only 2 of these are really solutions. So that gives us 2 of the points on the ellipse, precisely the ones with the slope 0, and now I can go through and do exactly the same thing for the other values. If I plug in dy dx equals 1, I get that equation, solve that for y, and plug it into my ellipse equation, and I get slightly more complicated values for x, but they're not too bad, and again the discriminant pops out. And compute the corresponding y values, and then we have the 2 points where the slope's 1. And we do the same thing for minus 1. Just scroll this up, and this is the equation we get for slope equals minus 1. I'll solve this for y, plug that in, and the roots we get are these two x values, discriminant there, and we get the corresponding y values, another 2 points. And finally we come to infinity. Now this is a little bit different. You can actually read the values off from the equation that we got for the slope above, but instead of doing that, there's another trick that works equally well, and that is to compute the derivative with respect to y instead of x. They end up being reciprocal of each other, essentially, and so when the derivative with respect to x is infinity, the derivative with respect to y is 0. And so that just makes the computation a little bit easier. You can use the same method then, and you get this equation. Plug that in, and basically you get this here. So that's the final 2 points. Now these will be the points for the start of our segments, and it might seem like a lot of work to go through all of this just to compute these, but in the end it's going to save us a lot of time because we have an algorithm for drawing segments that are like this. And so basically that's all there is to it. We've got a little bit more work to do. We still have to figure out the constants to use with our algorithm for segment drawing, and also the starting values, but that's something we can look at in another video. For now, I want to show you this really cool software that I found. This is software on desmos.com/calculator, and I don't know anything at all about these guys, but if you know the authors, then give them a shout and let them know. This is actually pretty good. I don't know about you, but I find software these days is very often just broken. It either is really hard to use and not intuitive, or it just has lots of bugs in it. And so far, there's just nothing I can think of that I actually want to do with this program that I haven't been able to just figure out without any instructions at all. And it hasn't crashed or died in any way, so I'm very, very impressed. At any rate, basically what it does is it lets you put equations in, and then it will just plot them, and you can zoom in or out just by pressing plus or minus here. And basically we can use this to see how our ellipse behaves. I put in the equation of our general ellipse here, centered at the origin, as you can see. And there are four coefficients, A, B, C, and F, that we can fiddle with and see how it changes the shape of the ellipse. So the first thing is that F just changes the size of the ellipse. Whatever it is, it just makes it bigger or smaller. So that's the behavior of that. And let's take a look at C, and at least for this ellipse, it just makes it higher or shorter. And let's take a look at B. This seems to sort of switch it from one orientation to another orientation. And it sort of rotates around a little bit in the middle here, you can see, but basically that's what that one does. And this one here looks like it's just changing it in that direction. Now, the interesting thing is that if we set b equals 0 here, we get the equation for the standard ellipse. So that's what I've got here, and that's why when I change these, I'm basically just changing the semi-radii. If I switch b to a different value, it doesn't quite work like that. You'll see there's a little bit of rotation as well as I do it, and it should be the same pretty much for this one as well. Now, what happens if I set it to some weird values? In fact, I'm going to do this deliberately in a particular way here. I'm going to set b to 2, since I know these values will work, and I'm going to set a to 1, and as I move c towards 1, you'll see something interesting happen. So, getting very close to 1 now, 1.1 and 1. You can see that I just end up with straight lines. Now, why did that happen? Well, b squared minus 4 times ac is 0. That's our discriminant. So that's the limiting case of the discriminant. Now, for this particular equation that we're working with, you won't get a parabola here. You'll just get 2 straight lines. But if I take it beyond this value, then you can see that I actually get hyperbola. So this is when the discriminant goes positive. So basically, this little gadget allows us to demonstrate quite a lot of interesting behavior, and actually there's a lot of different experiments that we can do with this that are actually going to help us to figure out how we're going to do our algorithm. And so in the next few videos, we'll probably be back at this little application a few different times to explore various things. One of the things that's going to go wrong in our algorithm is some of the values that we're going to use are going to get extremely large, and they'll be extremely sensitive to changes in input. So in other words, we'd need very high precision as well. And that's something that goes wrong very often with ellipses that are around about at a 45-degree angle. So by that I just am talking about the axes. And when they're long and thin, the algorithms tend not to work very well in that case. And that's actually something we'll be able to demonstrate with this piece of software. We'll be able to see at exactly which point things start to go bad. So I think this is going to be a heap of fun to play with. You can do much more than ellipses with it. It figured out itself that I was drawing an ellipse here, by the way. I didn't put that in. So you can put in pretty much any equation you want here and plot it and see what it looks like. Very, very impressive piece of work.